Hello, welcome to another Cosmology Talk. Today we have Song Huang, who is an assistant professor at Tsinghua University, and Alexie Leauthaud, who's a professor at UCSC. They'll be talking today about galaxy clusters, which are, I guess, a somewhat forgotten small-scale probe of cosmology. Most clusters aren't subhalos of a bigger halo. They're the biggest halo in their environment, which means if we know a cluster's mass, we kind of know the primordial fluctuation that produced it. And then via lots of calibrations to halo mass functions, we can learn about the early universe. So measuring the mass of galaxy clusters is absolutely crucial. And Alexie and Song used the Hyper Supreme Cam Subaru survey to use the outer stellar mass in the edges of the halo as a proxy for mass with great results. So welcome, Alexie and Song. Do you want to tell us what it is that is described in the paper you're talking about?
So in this paper, we studied the selection of galaxy clusters in optical survey. So massive galaxy clusters basically represent the most massive dark matter halos in the universe. They contain very unique and interesting cosmological information, and very important for galaxy halo connection studies. Also, very, very interesting for galaxy evolution study. In this work, we are trying to take advantage of the really deep imaging data from the hypersupercan survey using the 8.2 meter super telescope and its unprecedented weak lensing capability to basically evaluate the different optical proxies of galaxy or cluster finders. And we are trying to find one that is unbiased galaxy cluster finder using just the property of a single galaxy, which is quite challenging before. Our sample actually massive galaxies in the nearby low redshift universe. They're at redshift between zero point 0.2 to zero point 0.5, and they are really the most massive galaxy in the universe, more massive than 10 to 11.5. The key takeaway message, what we managed to find is that, interestingly, the inner region, by inner region, I mean the inner 10 to 30 kpc, the stellar mass within the inner region of the massive galaxy actually doesn't care that much about the dark matter halo. It's not a very good, it turned out to be not a very good dark matter halo tracer. On the other hand, actually, is the stellar mass in the very extended stellar outskirts. For example, if you measure the stellar mass between, say, 50 to 100 kpc, the stellar mass in the low surface brightness and extended outskirts turn out to be a very, very good halo mass proxy. When you actually selecting galaxy cluster using that, you get a pretty nice low scatter of a halo mass within a given number density bin. By comparing with n-body simulation, we think actually suffer much less from some really, really annoying systematic effect that has been bothering another really popular and powerful cluster finder, which is the richness. Richness basically the counted number of member galaxy. In specific, at least at the low redshift, they normally use the red member galaxies, or quiescent members in the clusters. Those are has a long successful history and still very commonly used, but it has some problem that really annoying, including the miscentering effect, which means when you look at a bunch of galaxies, sometimes you have to guess which one is the center of the dark matter halo. And also, because you're using the selection using optical images, they often based on either color or photometric redshift. So you are subject to very strong projection effect, which affect you, basically bias your galaxy cluster selection, and eventually will affect your cosmology inference or galaxy halo studies.
By projection effect, you mean that there are galaxies that are along the same line of sight, and because of the photometric redshift measurement, you accidentally think they're in the cluster, but they're not. So you get the wrong richness, or?
Yes, exactly. So basically, along the line of sight direction, you can basically misidentify some galaxy that are not associated with the galaxy cluster, but just in projection, they're close together and they have similar color. So you saw that it's a member. Turned out to be a really important problem for optical cluster cosmology. On the other hand, our method basically based on a single galaxy by its nature is suffer less from projection effect. If you have a way to handle basically massive satellite galaxy, which we believe actually we have, and we can do much better in the future. Yeah, so basically we find a really nice optical cluster finder that based on the stellar mass in the outskirts of massive galaxy, which can have a lot of interesting applications in future imaging and spectroscopy surveys, and eventually can help us build more accurate model for galaxy halo connection with massive galaxy. And we hope that it can really help cluster cosmology in the future.
So yeah, if there were only two things people are remembering of this talk or the paper 6 months from now, what would you want those two things to be?
The first thing is I hope more people remember that galaxy outskirt or the low surface brightness part of the galaxies can be really interesting. In the case of massive galaxy, we find there turn out to be historic richness. We call that. Actually, I think Peter Beruzzi from University of Arizona came up with that term. Basically, the mass in the outskirt actually is a proxy of the number or the mass of the galaxy accreted into the system in the history of the universe. It actually has a lot of useful information encoded in it regarding both gas formation and assembly of the dark matter halo. Can have a lot of interesting application in the future. And I guess the second thing is when people think about cluster cosmology, which I think will become more powerful in the future thanks to all the multi-wavelength surveys, not just the optical ones. Right now, at least in the optical surveys, the cosmology inference are heavily based on cluster find by richness. I just hope people remember there are really, really annoying and important systematic that it need to be dealt with, but it's going to be quite difficult to deal with in the near future. And Stellar-mass-based cluster finder, like what we propose here using the outskirts Stellar-mass, has a lot of potential, and some combination of both can take advantage. It's unique information and can be really powerful.
Why is this important and relevant in 2021? I guess the question that immediately jumps to my mind is why has no one thought of this and used this in the past? Is it that we need surveys that are as powerful as HSC and they didn't exist before 2020, 2021, or not? And where do you see this fitting within the rest of the cluster mess universe?
Yeah, it's a great question. I think this question has been studied on and off for a while, but the data sets weren't really of the quality to answer it with the same kind of precision that we did. So I want to point back to a really nice paper by Raina Bell Reyes, who studied the question of can we use BCG luminosity as a tracer of halo mass. I forget the date, but it was at least 5 years ago. But the problem was a lot of these studies use Sloan, and the Sloan Digital Sky Survey just isn't deep enough to probe these outer regions. And it's been shown by a number of people, including some work by Bernardi et al. And others, that you just can't model, you can't extract light from the outskirts very well. So the real novelty here was two things. One, the advancement of the HSC survey, which can probe the light profiles out to 100 kpc and really capture this outer mass, in combination with the weak lensing, which enabled you to tie it with the dark matter. So the combination of those two things was really novel. And Song and I kind of had this realization when we started working with HSC that these were two very novel angles to tackle, and we were looking to try to see whether this historical richness, so the amount of mass contained in the outskirts of galaxies, how well was that correlated with halo mass. We had the data set to do it, so we started tackling that, and it's taken 5 or 6 years to get through all the steps needed to get us to where we are today. But I think we finally show in our latest paper that the outskirt mass, the historical richness, is a really excellent tracer of halo mass that we want to continue to develop further.
I have a couple of questions that might just get answered as we go. So if you're planning on answering them as you go, just let me know. But one is why exactly the center isn't as useful as the outside. Because Song, you said you tested it and it isn't. Is it because things just kind of get messed up there? And the other one is, I guess there are two other big weak lensing surveys that people might know about, KIDS and the Dark Energy Survey at the moment. Is HSC kind of uniquely useful for this? Because I think you guys have a bigger depth than those two other surveys. But would they also be able to kind of use your technique in some way?
Yeah, the first one I think we're going to mention, but actually, I don't think in this paper we actually provide a direct answer because there's some things still under investigation. The thought is basically the massive galaxy has a really unique build-up process that its star formation history and the assembly history are kind of decoupled. Basically, if you look at the inner region of the galaxy, the star formed a long time ago, but it has already been there for quite a while. And later, the star formation has been quenched or shut down, completely shut down in the massive galaxies. What dominate basically there's no longer ongoing star formation. All the gain of new stellar mass come from the accreting small galaxies, and the stellar mass tend to build up in the outskirts of the galaxy. I think it suggests that if you look at the inner region, the stellar mass there are no longer correlate very well with the current halo mass. It may have some connection with the halo property, basically before the star formation has been shut down.
So you could kind of measure the history of the region by going almost like a tree. By going from the center further outwards, you're learning more and more about.
Yeah, exactly. So as I mentioned, so I'm not from cosmology background. So what my key interest in this is actually to study the connection between this galaxy and dark matter halo in different part of the galaxy and try to infer basically different aspect of the assembly of the dark matter halo or some unique property of the dark matter halo. Yeah, so we think it doesn't mean the inner region is no longer interested. It's just if your goal is trying to weight the current galaxy cluster, actually the faint low surface surrounding outskirt actually is more important.
Yeah, so the second question was, can you do this with other lensing surveys? And what I would say is the other lensing surveys have the lensing capability, but don't go as deep as HSC and don't have the same ability to measure the extended envelopes. However, we've been doing work with Jiaxin Li in a paper that's going to be on the archive shortly. So by the time people watch this video, it should be on the archive, where we've used a combination of dragonfly and decals, the imaging survey that will be used for DESI, and HSC to try to understand how more shallow imaging surveys, how well they probe the outskirts. And the answer that we find is that decals, which is a relatively short, shallow survey, actually has a pretty good ability to capture the outer mass. The key here is that you can't do this with just, the random data pipelines. You need to go back to the imaging data, custom process the imaging data because of the difficulty of sky subtraction around massive galaxies. So most of the current surveys, if you just take their default pipelines, including HSC, you're gonna have a lot of difficulty with this measurement. But if you make a custom made thing that's specially tailored to this problem, we find that in decals we can do this. And so we now have a new collaboration with DS to try to apply similar techniques to DS. And the next step in this research is to go to DS and compare with RedMapper, the richness based cluster finder. And we're going to use a combination of this outer mass and richness to try to disentangle some of these projection effects.
So should we get into the details now? What is it that you did in the paper in detail? How does one detect the galaxies and measure the outer edges? And
So here, just the title of the paper. Just want to mention that the paper has been submitted, and we just received a very positive referee report. So it should be no problem getting accepted very soon. Both the code and the data are actually in public. So if anyone is interested in this, they feel free to explore. Yeah, before getting started to the dark matter halo part, I just want to show people, especially I think some of the cosmology may not that familiar with the imaging data. And so here is image of a nearby galaxy cluster from the 2.5 meter telescope used by the SDSS survey. And here is the same data we get from the HIC camera on the 8 meter telescope. As you can immediately see, we see much deeper images. Not only we see more fainter object. If I go back and forth, you can see, look at the galaxy in the clusters, you can immediately see they're more extended and outskirt profile. So those are the exactly, as Alexie mentioned, those exactly regions that why HIC is better at probing the outskirt of the galaxies. So basically, for massive galaxy we're interested in, we can go measure, we call it 1D surface brightness profile. Basically, how does the surface brightness vary with the radii in elliptical apertures? Then we can actually use that to measure the light, luminosity within different radii or within each aperture. And we can also use that to measure the basically luminosity between different apertures, like the luminosity of the outskirt. And also, HSA is a multi-band survey, so we have color information that can help us estimate an average mass-light ratio that convert that into stellar mass. So basically, for each galaxy, we can understand the stellar mass distribution within the galaxy in 2D. And just a quick word for HSC project. Hope people can remember it as a really wide. It has just reached 1,000 square degree, and it's a super deep imaging survey, and they also have a great lensing capability. So wide, deep lensing survey. That is a unique advantage of HSC. Meanwhile, there's also another popular approach to basically select and estimate the halo mass of the galaxy cluster, which is using the richness of the red sequence galaxy or basically the member galaxy that appear to be on the red optical red sequence, or basically they look red, have the same color. Popular algorithm for this is like Red Mapper and Camila. They have been used for multiple imaging survey. They're really powerful and provide a lot of interesting results already. But as I mentioned, it has suffered from some important systematic effect.
Can I ask a quick, maybe slight, it feels like a silly question that I've always wondered about richness. There's only like 20 circles there. I mean, is richness normally a bigger number than 20?
This is for just for demonstration. I just eyeball a few galaxies that look right, and it's
So what is the normal value of richness that one might find?
it depends on the imaging survey you're using. Shallower images and deeper image for the same cluster, you can see different number of member galaxy.
I would say cosmology studies usually use richness between 15 and 40.
So that feels to me like it can't possibly have a particularly good resolution for the mass, right? Because from 15 to 40, there's only, what's 40 minus 15? 25 different possible values, whereas mass is obviously a continuous property. So you're kind of limited to 25 possible bins. Is that all like correct, or have I got some silly intuition here?
Yeah, in practice, something like RedMapper actually uses a probability. So there's a richness probability, which is continuous. But indeed, there is, a Poisson statistic here of limited number counts, and that will play into the scatter between richness and halo mass. And so ultimately, what you care about is having a small scatter between richness and halo mass, and we think we have a tracer that has comparable scatter.
Is it also comparable to something like, say, X-ray temperature?
Yeah, I guess that's one of the future direction we want to look at. Right now, we only have a very small sample of galaxy cluster overlap with a deep enough X-ray survey. Although the situation might change when the Euro Zeta and the full sky X-ray research release data, where the HSC survey also collaborating with the Euro Zeta people. So we're definitely going to look into this. Yeah. Yeah, so basically what we're going to do in this paper is we are going to use the galaxy length measurement as a judge to evaluate the different observables. For example, different measurement of stellar mass within the massive galaxy and the richness within the cluster as a halo mass proxies. So we call this a top-N test. The reason is that the logic behind it is really simple. So for example, here on the left side, I just show the kind of richness function of the red macro galaxy clusters from the HSC. And the right side, I show the stellar mass function of the massive galaxy from the same sample. If I make just a same number density cut, for example, if I say, let's select the top 100 richness cluster from the left and the top 100 most massive galaxy from the right. So the two sample will have the same volume number density. And we can go using the HSC lensing data to estimate their galaxy lensing signal. Basically, what we get is this so-called delta sigma profile, which tell you the total mass distribution around the cluster and around the massive galaxies. And here, in most of this paper, we are using, instead of this R times delta sigma, we still call it delta sigma profile. It's just a different representation, which in visualization would make it more sensitive to the variation of the shape in the inner region. So it's the same information. Basically, we can directly compare the different lensing signal from the same samples of massive halo selected by different optical proxies. So using HSC data, we can actually do this in different number density bins. So it's no longer just top 100. It's basically something like top 100, top 100 to top 200, top 200, top 500, something like that. So in this paper, we are exploring in total of 4 number density bins that cover pretty large range. So you were just, so Shaun, you were interested in the range of the richness. In HSE, actually, if you're using Random Mapper, you basically can afford something like richness from 5 to 100. Although at the low richness region, it will be much, much more uncertain.
Just to clarify something, the y-axis, sorry, x-axis says log of lambda, but that just means that the axis is spaced logarithmically, but where it says 10, that's actually lambda equals 10, not log lambda equals 10. Is that right?
Oh, right. That's a really good point. Actually, yeah. Yeah, so the reason we can do this is actually all the underlying cluster finder are relying on scaling relations with halo mass. So we call them cluster. What we really want in cosmology is just the massive dark matter halo. So we always basically assume, for good reason, that there is pretty nice scaling relation between the halo mass and a certain observable. For example, we know the halo mass and the richness has a pretty nice relation. We know the halo mass and the stellar mass, the central galaxy, also have a relation. The different scaling relation, they often represent in the log linear form, and they are characterized using, basically, you can simply using a slope and a scatter. So different observable, they follow different relations. So here I show 3 different observable. They follow this just artificial Mach scaling relations with different slope, which is alpha, and scatter, which is a sigma. And although I show this halo mass and observable relation, in observation, we select massive halos using observables as tracers. So for example, we can select the top n different observables as highlighted by the darker color region. They correspond to a different underlying halo mass distribution. And this distribution, the mean halo mass and the scatter of halo mass, depend on basically the shape and the scatter of the underlying scaling relation.
Can I try and just decipher this plot for a second? So if let's fixate on the green ones for a second. The everything that is green follows the dash dot green scaling relation. And what you're saying is that if you make an observational cut above a certain value of whatever the green observable is, that you then get the dark green dots, and that clearly those dark green dots don't follow that scaling relation. Is that? And then the same for the red and for the black. Is that right?
Yeah, so in this case, we can see basically in terms of the halo mass distribution of a certain sample selected using observable, there's a degeneracy between the scatter and the slope. So for example, here we know the red one and the green one doesn't follow the exactly same scaling relation, but basically there's a trade-off between the steeper slope and the smaller scatter. If you're using the same number density card, you end up with the same very similar halo mass distribution. And if you examine those halos, we actually got this from n-body simulation, but so we extract the lensing signal. You can see the lensing signal almost exactly identical. Meanwhile, the blue one, because it has both steeper slope and the smaller scatter, both are very nice qualities we like when we're trying to build a galaxy cluster finders. In the same number density sample, the underlying halo mass distribution has a higher mean halo mass and a lower scatter, so end up with a lensing signal with much higher amplitude. This basically tells you that for a given sample, its lensing signal can tell you something about its underlying halo mass distribution. And given n-body simulation, a simple assumption of a scaling relation, we can actually try to infer the scatter of halo mass using observed the lensing signal. So that's exactly what we did. We based on the multi-decaplan 2 and a small multi-decaplan simulation. So using the massive halos into simulations, we assume a stellar mass halo mass relation that can basically explain the basic observables in HSE, like the stellar mass function and the correlation function of massive galaxies. And based on that model, we can predict the lensing signal in the predefined number density bins. Here are the bin 1, for example, the bin 1, bin 2. Basically, as the scatter of halo mass within each bin become larger, you can see that the amplitude of the lensing signal decrease. And also, as you look at the red panels here, it will also reflect in the halo mass distribution. So the dashed line here basically show you when the scatter of a halo mass within the bin is 0.4 dec, and the highest line basically indicates there's no scatter. And the right side basically show you the very clear contrast of the halo mass distribution. So yeah, in observation for given observable, for example, here I'm using the stellar mass measured within 150 kpc aperture. We can select the massive galaxy into different number density bin. We get their stacked lensing signal. Then we can compare with the n-body simulation prediction because we are using the same number density selection. So basically, we can find a kind of a best match lensing profile, which corresponds to a certain scatter of halo mass within that bin. This kind of a pretty simple and straightforward fitting or dirty sigma profile matching procedure can help us infer the scatter of halo mass within each bin based on n-body simulation. Again, this is a perfect profile. This is the best fit one. And you can, again, the right side show you the inferred halo mass distribution. So I think Alexie just mentioned that one of the reasons that we can only do this now is not only because there's a deeper image from HSE, is because we in a a series of the previous papers, we have dealt with all the photometric issue. If you try to carefully measure the outskirts stellar mass, there's a lot of steps you have to go through to make sure your image has the correct background subtraction, you overcome the contamination of nearby object. So if you just use the default photometry of the galaxy provided by the photometric pipeline, in this case, this is the model, photometric model called C model. For people who are using SDS editor should be familiar with this. It's a pretty popular and flexible photometric model for galaxies. However, in this case, so what we're looking at is this. In each of the bin, I compare the samples of massive halo selected by stellar mass based on the default pipeline photometry, HSC pipeline photometry, and our carefully measured stellar mass within the 100 kpc. As you can see here, basically the 100 kpc stellar mass one has a much higher amplitude in their lensing profile, which indicates the underlying halo mass distribution have higher mean halo mass and lower scatter. Basically, the C model, the default survey photometry, actually does a poor job recovering the total flux of the massive galaxies. And if you try to study galaxy halo connection and you're using the default photometry, it's going to impact your result.
Can I ask to clarify one thing on this? So people shouldn't be thinking that the cross data points are really far away from the gray band, because if you were to do a new best fit value of sigma, you would get a new gray band. So it's not the fact that it's a bad fit to the data, it's just that it's a smaller signal that the crosses are below the circles and they would have their own gray band, but it's just not getting as much information.
Yeah, so there's a lot to infer from the shape, but generally speaking, what you should focus here is the much lower amplitude, which indicates basically the mean halo mass of the sample is much lower than the gray one. Yeah. Okay, so basically we now have a series of different observables. Now in the four bins, we can basically infer how does the scatter of halo mass in each bin vary with the number density. So right now you're looking at from the left to right. Basically, it's a lower halo mass to increasingly higher halo mass. And the y-axis is the scatter of halo mass in each bin. So lower value means it's better. If we want to find a better cluster finder, we want to find ones with a smaller value on the y-axis. So here we are actually comparing different aperture stellar mass, basically stellar mass enclosed within different apertures from 10 to 300 kpc. You can see that clearly the inner 30 kpc, they all have pretty high scatter of halo mass in each bin, and basically there's no trend with the halo mass or number density. However, when you look at, say, the green line, which is a default measurement here, which is the 100 kpc stellar mass, the scatter is much smaller than 30 kpc, and you start to see as you go to higher and higher halo mass, the scatter become lower. Meanwhile, we also estimated the stellar mass within different definition of the outskirt of galaxy using, for example, the stellar mass between 10 to 100 or 30 to 100, 50 to 100 kpc. What we see here is, for again, using the green dashed line as visual reference, we see that when you actually just focusing on the outskirt of the galaxy, the scatter become even lower than the total stellar mass, which indicate actually the outskirt of the galaxy is a better halo mass proxy than the total stellar mass of the galaxy. And you can actually see this when you compare the lensing profile, the dirty signal profile directly. So here the solid line is the stellar mass in the outskirt. I'm using the preferred observable, which is the stellar mass between 50 to 100 kpc. And we compare to the total stellar mass within 100 kpc. Again, maybe it's not that obvious in the first bin, but in the second bin, you can see the lensing profile of the outskirts stellar mass selected sample becomes systematically higher. And in the following higher number density or lower halo mass bins, this is the same, and it becomes more obvious that the outskirts stellar mass remain the better halo mass proxy than the total stellar mass within a very large aperture. Yeah, so this is a kind of the key result of this paper, which is the outskirt of the massive galaxy is a better halo mass indicator than the total stellar mass. So now we actually compare different flavors of observables as halo mass proxy. And we'll also do the same for the two popular red sequence cluster finder, which are the red mapper and Camilla here. As you can see, the takeaway message is first, the C model is really bad. So be really careful if you want to study the galaxy halo connection of massive galaxy. Just maybe don't use the default photometry unless you know what's going on. Another thing is the richness still have really, really low scatter, still outperform our outskirt cluster finder, especially in bin 1 and bin 2. They indeed have clearly a lower scatter value. In the lower richness or lower halo mass regime, we can see that the blue one, which is the outskirt stellar mass, they start to become really getting really close to richness or even better. This means that really low richness regime, richness measurement become much, much more uncertain, but the outskirt stellar mass measurement can still be pretty stable. If we just look at this picture, we may infer that, okay, outskirts stellar mass may be interesting, but still not as good as the richness. So not so fast. Although the richness cluster finder like red macro Camilla, they still have pretty low scatter value inferred from our very, very simple model. If you look at actually their best fit profile, you can see, for example, the left side is the red mapper, middle panel is for Camilla in the first three bins. The gray ones represent their best fit model. As you can see, there's a clear residual, and the model cannot really fit the observed lensing profile that well. Here, I should mention that our model is really simple. We're just directly using the massive dark matter halos in those embodied simulations. We do not aid any miscentering effect. We do not aid any projection effect. So a lot of the systematic that are faced by these richness cluster finders, we do not have that in our model. So that could be part of the reason that our model cannot fit their data. And the third panel is the key here, which is outskirt stellar mass. And here you can see our model, very simple model without miscentering and projection effect, can already explain the stack lensing signal observing HSC very, very nicely. So this is a very strong indication that when we actually using the stellar mass measurement of the single massive galaxies, it suffer less from the systematic that faced by richness cluster finder, which are miscentering and projection effect. So although maybe in terms of the scatter value, the outskirt stellar mass is already pretty good, but not as good as the richness cluster finder. But we do have some really unique advantage that we can explore in the future. Yeah, so in summary, I think this slide summarizes another key result of this paper, which is the unique advantage of the stellar mass-based cluster finder, like the outskirt stellar mass, which is they can be explained by a very simple model, which is basically a scaling relation between halo mass and the stellar mass with just a log-log linear, just the slope and the scatter. This actually surprised a little bit because we know when we build the toy model, there's no any additional systematic effect. We worry that it cannot fit any profile. It doesn't mean they don't suffer from any miscentering or projection effect. It means that it's much less than what the richness cluster sample suffered. Yeah, so that's really important advantage.
I was definitely wondering before this slide whether you just had so much freedom you could fit kind of anything, but clearly you don't.
Especially in our case, we do see that there's we call it a 1 megaparsec bump. That's definitely not an official term. But when we compare the lensing profile of the richness cluster to the best fit model, it always seems to be dipping below the best fit model in the inner region, but become higher around 1 megaparsec, which is an interesting regime because 1 megaparsec is kind of the boundary of the cluster halo, or the boundary between the one halo and the two halo term. So there's definitely something can be explored here. So actually modeling this is actually very difficult. There are some pioneering work in trying to evaluate the impact of projection effect on the cluster lensing signal. So there's a work by Tomomi Tsunayama. Basically, they build a mock red macro cluster finder using embodied simulation, and they try to select sample by richness and select by true halo mass, and they compare the difference of the lensing signal into different richness. So here, different colors mean different richness bins. As you can see, the y-axis is the observed lensing profile of the richness select sample compared to the true halo mass selected one. There's a clear radio-dependent trend, and it can bias the lensing signal to 10 to 20%, and it also have impact on the projected autocorrelation function, which unfortunately we don't have right now, but it is also another very important exam of the projection effect. But if you just look at the lensing profile, at least right now, the predicted one, it doesn't solve our problem because in their case, you can see the deviation is much stronger in the outer part of the lensing profile, which is understandable. But in our case, it's more like the 1 megaparsec region of the richness clusters become systematically higher. So again, this is definitely one of the future directions we need to look into. I would say one of the reasons that modeling the projectile is super difficult is because right now the richness selection based on they need to use galaxy color. So it's called red mapper. Basically, you try to select red galaxy, and galaxy color is very difficult to model using whatever model, hydro simulation, semi-NAC model. It's not that easy to get the color right. Hence, you will not be able to build a very accurate mark cluster catalog based on embodied simulation you want and trying to examine all the systematic involved in richness cluster finder. On the other hand, galaxy halo modeling have been trying to modeling the stellar halo mass relation forever. So if you just involve the stellar mass of a galaxy, it's relatively easier to get it right and build a mark catalog based on embodied simulation.
As someone who's a bit naive about this, what is it that dictates the color of a galaxy? Is it like age, metallicity, or is that the problem? People aren't really super clear what primordial gas will become a different colored galaxy.
So basically, all the cluster central and a lot of the member galaxy, they're already very red. It means there's no ongoing star formation. And the color actually pretty similar. But if you observe using the same band or same filter, red stream filter, the cluster at a different redshift will appear in different color. So basically, the red mapper, they're trying to use the almost constant nature of the red color of all the static galaxy within the cluster, and they use it as a very cheap photo Z estimate. In the observer image, it's actually the redshift of the system determine the color a lot. But for the intrinsic color, yes, it's determined by the overall stellar population properties, namely the stellar age and the metallicity. I think for red galaxy, actually, the metallicity matters a lot in the low redshift universe. Okay, yeah, and one last thing I want to mention is actually answer one of your question earlier, why stellar mass in the inner region doesn't care that much about the halo mass, but the outskirt does. So this relates to the current picture of the massive galaxy formation, which is this called two-phase formation scenario. It basically suggests that a high redshift, a very active star formation or starburst form a very dense core that become the progenitor of the present-day massive galaxies. But after certain redshifts, say redshift 2 or 3, certain process, likely agent feedback, shut down the star formation, that the system become quench, and later it just grow by accreting smaller systems. So we often separate the star assembled into the galaxy in those two different phases or two different epochs. And all the stars formed within the progenitor halo, we call that in situ stellar mass. They tend to dominate the stellar mass in the central region. However, the accreted stellar mass, they tend to dominate the outskirt, and we call them ex situ. Also, we actually don't include this figure in the paper, so it's kind of a tease here. Basically, we examine the massive galaxy at the same redshift from embodied simulations and the semi-empirical model. Here, is the universal machine model by Peter Beruzzi. For those models or simulated galaxies, we can actually physically separate their stars into the in situ and ex situ region and examine their relation with halo mass separately. What we find in common is that actually the ex situ stellar mass has a much better correlation with halo mass than the in situ one, and the ex situ stars dominate the outskirt. So if you can imagine, when we measure the stellar mass within 50 to 100 kiloparsec, it's kind of give you a not perfect but pretty good proxy of the ex situ stellar mass. That's why actually it does better than the total stellar mass of the galaxy, which involve aiding the in situ part of the galaxy, and that part of the stellar mass actually has a not very good relation with halo mass, so actually it makes it worse. And if you trust this hydro simulation and the semi-empirical model, look at the top panel, it actually, if there is a way to actually separate the ex situ stars from observed galaxies, you can form an even better halo mass proxy than just measuring the outskirt stellar mass, because the ex situ stars actually follow a scaling relation with a slope very close to the richness. which is basically close to 1. Those are really nice properties we want to have in cluster finding.
So the gray data here is your stellar mass one, but not fitted just to X situ, but it's fitted to the whole.
Not fitted. So that's part of the reason this figure is not included in the paper. It's not a fit. It's actually guess. So we just roughly as a next step, we are going to try. We're trying to constrain the halo mass stellar mass relation for the outskirts stellar mass directly, and by then we will have a more accurate visualization of the scaling relation.
Where to next? Where should the cosmology community maybe be thinking about, and what do you, as a collaboration, what are you moving into next?
I think there's a lot of different directions to go in that we're exploring right now. So, one is going back to simulations, hydro simulations, and trying to see whether hydro simulations make the same prediction. The inner mass having a lot of scatter and the outer mass having a lot of scatter to help aid that physical picture. Secondly, is trying to push this to be a fully fledged cluster finder method and to get cosmology constraints on the growth of structure. And to do that, we're pursuing a couple of angles. One is we have an approved DS plus HSC project to do a comparison in the overlap between HSC and DS between the outer light tracer and red mapper to see what we can disentangle there. And then third, the angle that I'm really excited about, which I think is the angle of the future, is really moving towards a genuine multi-wavelength understanding of clusters. So the outer light is just one tracer of the assembly history and the halo mass, but in reality, I'm kind of have a hunch and I'm convinced that we can build even better traces if we combine the outer mass with a little bit of richness, with a little bit of X-ray. And to do that, we need to understand the covariance between all of these observables and how to combine them in a way that we can get the best halo mass tracer. So that's going to require a combination of theoretical work using hydro simulations, understanding the covariance, and observational work to see whether the data support the same covariance as predicted by the theory, and do this top end test again with other optimized tracers. And I think that'll be the way of the future. So that's the direction I'm really excited by.
That is very exciting and also very ambitious. You have a kind of feeling on timelines. So the DES plus HSC collaboration to turn this into a cosmological probe, would that be like a 1 or 2 year thing? And then I guess the multi-wavelength thing, would that be, I don't know, a few more years than that?
I think it's coming very soon. So I think turning it into a cluster probe is, maybe 3 years of work, depending on how many people work on it, obviously. And then on the data side of things, I work in the DESI collaboration. DESI's getting redshifts for, millions and millions of galaxies. And DESI's overlaps with ACT, the Atacama Cosmology Telescope. We have a joint agreement with them now. It also overlaps with eROSITA. So we're starting to get, fairly deep imaging surveys with weaklings and capabilities, with redshifts from DESI, with SZ measurements from ACT and X-ray from eROSITA. And so I think the data are there. And so we just need the the tools in place to study this.
So for people who might not quite realize why ACT is relevant, it's because the CMB would scatter off the hot gas in the center of the galaxy cluster, and that's the SZ effect, Sunyaev-Silvovich effect. Is that
Exactly. So another measure of the gas content. And so combining the gas content with the galaxy content, which is what we've talked about today, and the dark matter content from weak lensing, I think is the way of the future.
so? It sounds like if there's an interested postdoc or PhD student, they should get in touch. It sounds like there's work that can be done. That
There's lots of work to be done. Absolutely.
Yeah, so the first thing is the DESI survey, which is going to really help us. Alex already mentioned we're working with a graduate student, first year graduate student, Jiaxuan Li at Princeton, basically show that although the legacy survey or the decal survey used by the DESI is shallower than HSC, if you do the background subtraction and everything very carefully, this is done using a very nice photometric pipeline by John Mostakas. You can also measure the stellar mass between 50 to 100 kpc statistically accurate. I mean, individual galaxy, the measurement is still worse than HSC because it's shallower. But statistically, if we have large enough sample, it actually is good enough. And the Alexie survey covered more than 5,000 square degree of the sky, much larger area than HSC. So that gave us a lot of additional data. And the DESI is going to observe the area, which will help us really separate using real spectroscopic redshift, separate the central and the satellite galaxy, and help us build a better model, and eventually use stellar mass based or we are actually trying to combine the stellar mass based and richness based cluster finder used in the Alexie survey and trying to constrain cosmology model. And Alexie also mentioned this multi-wavelength understanding of a galaxy cluster, which is really important and ambitious. But right now, I think I'm just focusing on a simpler question, which is for each cluster, we have this different stellar mass measurement and richness. Understand the covariance between those are already an interesting question. Basically, at the same halo mass, why some halos basically have higher richness than the other. So a lot of people will tell you that clearly tell you something about maybe the concentration, the formation time, even the even larger scale environment of the dark matter halo. So from those, if you understand the covariance between richness and mass, it gives you a lot of additional information. You can move beyond just the stellar mass. You can understand basically the whole assembly of the dark matter halos and even study something like the assembly devise of the massive halos, which are very interesting.
So, yeah, what work being done in cosmology at the moment do you think is particularly underappreciated by the community as a whole?
I think it's harking back to what I said earlier, so a bit of a duplicate, but I think this multi wavelength understanding of clusters has not been studied in great detail. There's a few really pioneer papers on this topic, but I think it hasn't been studied in great detail because we haven't had the data sets to do that yet. But those data sets are coming, and I think that will really enable us to understand clusters in ways we haven't before and to make them a really excellent probe of the growth of structure. And the reason we need to do that is because we need to probe the growth in addition to the expansion. The expansion is quote unquote easy with BAO and other such measures, but the growth is very difficult. We have weak lensing, RSD, and clusters. We know it's very difficult. It's going to be a complex challenge, and we need to, understand clusters at the level to make the necessary growth of structure constraints. So I think that's an underappreciated angle, I think.
And galaxy clusters are also probing a different distance scale to all the others, like a much smaller distance scale. That
Right. So if you're interested in probes of modified gravity, there's a lot of tests of modified gravity on cluster scales that are very interesting. But again, we have to understand the selection effects on how we're selecting these halos. Yeah, so I think all of these things will become more precise as we have the data to really give us a multifaceted picture of clusters, not just a single wavelength picture, which is what we've been working with so far.
you said there are a few pioneering papers. Do you want to just mention what they are in case people are keen to look into that?
Yeah, there's a few really cool papers that I appreciate from Gus Everard and collaborators. There are some papers by Farahi et al. Looking at the covariance between different probes and also trying to look in that in data. There was a recent Nature paper by Farahi et al. So it's a topic that a subset of people are looking into, but I think there will be more and more efforts in this direction with the deluge of overlapping surveys that are about to come our way.
I'm constantly amazed by basic cosmology already pursuing, let's say, 1% constraint of certain parameter and 0.5 constraint of that different parameters. While observer galaxies, every time when I say basically the uncertainty of the stellar mass of a galaxy is like 0.1 DAC or 0.15 DAC, I'm really afraid because I know the underlying systematic uncertainty is larger than that. So basically, if your cosmology probe involved galaxy, pay attention to some of the issue in the data. I know SDSS have a very, very great impact in cosmology and galaxy halo connection, but a lot of people directly basically use the catalog provided by SDSS. SDSS is a shallower survey, and in some sense, it's reasonable to do that. But in HSC in the future for LSST or Roman Space Telescope, data will be deeper, better, but also more complex. There's a lot of additional systematic. Background subtraction will be much harder. Image deep blending will be much harder. When you reveal more complex outskirt structure of the galaxy, photometric modeling will be more difficult. How do you do that? And what's the potential impact in the selection of galaxy with different property for your cosmology probe? So those questions need to be taken care of. Yeah, basically pay attention to the to galaxy mode.
Thanks everyone for watching. If you like this, please do click subscribe and click the bell if you want to be notified of new videos, and click like to help with YouTube algorithms, and share the channel with colleagues. If you have any questions or suggestions, leave a comment. And thanks again, Song and Alexie, for the great talk.
Yeah, it's been really fun.
Yeah, thank you so much, Shaun.